Southtown. And we're Team 1, and our project is based on the hydrothermal weed cleaner. So weeds are a common problem every residential owner faces daily. The damages it includes is structures, insect pests such as an increase in mosquitoes, that leads to an increase in disease, such as malaria, dengue fever, West Nile virus, and also it includes land degeneration. So pesticides are a common method to eliminate these weeds. However, the harsh chemicals inside the pesticides can cause damages to the pets, children, and underground water pipes. So the hydrothermal weed cleaner will use water supply line from the outside water line, and it would instantaneously raise the temperature of that water and eliminate the weeds and the use of pesticides. We also want to motivation, I'm sorry. The emphasis that we have on this project is green energy solutions, and we also want to create a system that's concentrated on the global safety of the community. We also want to halt an increase in insect pests, disease, and land degeneration. So the objectives of this project is to create an eco-friendly machine that's cost-efficient and effective, and develop a system that will be used by people of all ages, including elderly people incapable of physical tasks. We also want to manufacture a system that can be used in a variety of environments, so we want to make it as portable as possible. So the literacy survey. There's a different amount of different technology used for the elimination of weeds, and one of them is the shark steam mop. The problem with this one is that it's only used for indoor floors, and with that, it only affects the surface of the weed. It doesn't affect the root of it. So the weed will continue to grow, and the price for that is $117. The vapor mower is another technology that's similar to the shark steamer, and it uses a 1.6 liter water reservoir, and also only affects the surface of the weed, not the root. And the weed techniques. This one is actually particularly only used for weeds. However, it's also used only steam, and the only disadvantage for this is the price tag, which is $10,000 to $25,000. So the industry standards. We want to follow the ASME Code of Ethics, the EPA, United States Environmental Protection Agency, Chapter 6 Water Act, the STM, American Society of Testing and Materials, and the Broward Electrical Code. So the project goals. We set different variables in the project to see if our system can maintain that goal. So we set a distance for 1.5 feet, the time within 5 seconds maximum, and the temperature at the max of 95 degrees Celsius.
Thank you, Peter. The design part. The hydrothermal weed cleaner has three main components. The first component is the water control valve, the handle and trigger, and the heating element. This is the concept design. We have a handle to the user can easily handle the equipment, and as a trigger that controls the water line through the heating element. The prototype done first that we designed with one heater, and then first we use the shower steamer heating element, and then we use 2000 watt heater like this one, and we use the temperature gauge for the output temperature. But for the first prototype, we didn't get the target temperature of 95 degree, so we developed the prototype 2. The prototype 2 has one control valve, control the mass flow, and it has two heaters. One is 2000 watt and one is 500 watt on the top. These are the parts for the prototype 2. The two heater, one is in the bottom, it has large area, and the top one has small, the 500 watt and small area size. And the ball valve that we use for control the mass flow, and the trigger that control the flow rate. This is the completely assembled model of our prototype, this one. It has a pressure gauge. We put the pressure gauge in order to control the city water pressure from 45 psi to 10 psi. And we use the temperature gauge to analyze. It's an analog temperature gauge to check the output temperature. And some of the soil study that we did, we checked the thermal study for the heating element, and also we did the thermal study for the components. So the future development, the prototype 3 that we developed, This has some more advanced parts like the digital thermometer, and it has a thermostat inside, and also the overflow gauge also in that prototype. The design safety. The pressure reducing valve, like this valve, we use for the control the pressure from the city water, and also we use the surge protector for this type surge protector in order to protect the equipment also from the household, the circuit breaker. And trigger also, this one has the safety mechanism for the child. Global learning design. The different voltages are taken consideration, the 110 volt and 220 volt for different countries. These countries, the 220 volt using countries and 110 using countries. And also we use different manuals for different in 3 languages, English, Japanese and Hindi, for the easy use of the end user. And also SI and the English units has also used for this prototype. This is the manual in English, this is in Hindi and Japanese manual for this prototype.
So we tested the prototype on 3 different kinds of weed, basically dollar weed, St. Augustine grass, and blackroot plant. This is some of the very few equations that we used during the analysis and the Reynolds number constraint that we were following. This is the experimental data that we obtained through the experiment. The 90-degree valve opening is the time when you have the maximum volumetric flow going through the prototype. And as that angle decreases, you have a decrease in volumetric flow, the velocity, the mass flow rate, and also the Reynolds number. These are experimental calculations. Further, you can see there's a very linear relationship between mass flow rate and the volumetric flow. So in order to make any changes in the prototype, you have to make sure the mass flow rate and the volumetric flow rate go simultaneously. This is the direct relationship between the mass flow rate and opening of the ball valve angle. It is sort of a polynomial graph, and you can see that as the ball valve angle is increased, volumetric flow increases, and also the mass flow rate is increasing throughout. Now, a relationship between temperature versus the mass flow rate shows us as the mass flow rate decreases, we have an increase in temperature. So that's the scope of this project, that we have to reduce the mass flow rate to a certain optimum point that we could attain a temperature of around 95 degrees Celsius. This is the correlation of valve opening angle versus temperature, pretty much the same, very linear at the beginning, and between the change of a 30-degree angle to a 20-degree angle, we have an increase in temperature of 100 degrees Fahrenheit to 200 degrees Fahrenheit. Using the Bernoulli equation, we will try to get the pressure gauge differences throughout the system with the inclusion of ball valve, with the inclusion of pressure reducing valve. This is one of the equations that we use for the minor losses. And the minor losses would also include the T-joint. And after the introduction of a pressure reducer in the system, there is not much of a pressure gauge difference throughout the system. We have 12 as a theoretical pressure, and we have experimental pressure of 12.5 throughout the rest of the system. So pressure does not play a big role after the introduction of a pressure reducing valve. This is the basic equation we use for heat transfer. As the mass flow rate increased, we have a heat transfer. We have a decrease in heat transfer, and finally, at 2,000 watts, we'll have this mass flow rate. And this is the relationship between the heat transfer versus the mass flow rate. But that is the theoretical part of it. Experimentally, we had to use another heater of 500 watt to get a temperature of 93 degrees Celsius, because experimentally, when we used just the 2,000 watt heater, we weren't able to get 100 degrees Celsius. And using those heat transfer equations, we are able to calculate approximately the surface temperature of the 2,000 watt heater, which is almost 146 degrees Celsius, and the surface temperature of the small heater, which is approximately 111 degrees Celsius. This is the relationship we derived to calculate the heat losses throughout the system. This is the mass flow rate at different ball valve opening and the heat loss throughout the system. This is the heat loss comparing the heat loss in the 2,000 watt chamber and the heat loss in 500 watt chamber. As you can see, there's more heat loss in the 500 watt chamber. This was the total cost of our entire project, $202. a basic breakdown of our responsibilities as a group, a quick review of the God chart. So at the end, we weren't able to get the target temperature of 95 degrees Celsius, but we came pretty close to 93.3 degrees Celsius. But so some of the improvements that we would like to make in this project is like the weight of the project, which is around, at this time, around 32 pounds. But we would like to reduce it to 25 pounds. We're reducing by changing the material. Right now, we're using galvanized iron.
Hello, ladies and gentlemen. My name is Peter Garcia. We also have Prajeet Nair and Saad Khan, and we're Team 1, part of the hydrothermal weed cleaner. Right now, I'm showing you our circuit breaker that we did for the heating elements. And now, I'm going to show you our hydrothermal weed cleaner device. As you can see here, we have the heated water being dispersed from the nozzle. And we also have a temperature gauge placed here. And as you can see, it's right above 200. And the type of weeds that we're going to be applying it to is, the first one is the dollar weed. As you can see, some of the heated water has a little steam, so it's close to boiling point. And the second weed that we're applying to is the one next to it. And the third weed that we did was actually St. Augustine grass that we did earlier in our experiment, and this resulted 1 day later. So once the hydrothermal weed cleaner is applied to the weed or grass, it takes about 1 day for it to turn brown and die out. And that concludes our presentation. Thank you very much.
So that was the effect on the dollar weed a day later. And again, St. Augustine grass. And that concludes my presentation.
Why do you think you couldn't get 95 degrees?
We can get that 95 degrees because the system right now it's not insulated. We are having heat losses. But what I had personally problem figuring out is like the heat losses are not that much. It should still work around 2,000 watts, but we still had to introduce a 500 watt heater to get it to 93 degrees Celsius. Whereas theoretically, from our calculation, it looked like 2,000 watt would be enough to get it to 100 degrees Celsius.
But the calculations were assuming no heat loss, right, to the surroundings?
No, it was.
It was?
It was.
So you're taking into account the conductive heat and the
The
radiative
conductive
transfer?
and the convection, free convection that's happening.
Okay. You got radiative as well.
Yeah, maybe that, but I
Uh,
would,
Now, what about when you stop the trigger and the water's still there, does the heater still keep heating?
yeah, it does keep you.
So it'll go past the boiling point, right?
It would go
Yeah.
past the boiling point, and that's why we have a user manual explaining that this should not be done. Heater should be switched out before the trigger is.
Yeah, I think maybe you could have put a switch on the actual trigger.
Actually, that's where our prototype 3 is. We have a thermostat placed inside that device. So that way
It'll cut off.
Exactly,
Yeah.
electronically cut off.
Yeah, so,
What happened was during our initial research of the project, we couldn't find a heater like that which would actually have a tank and it will hold the water for a minute or two and then release
Sure.
it instantaneously. We couldn't find a heater like that because, first of all, we weren't gonna make something like that because at the end of the day, it's water and electricity side by side. So we
well,
didn't-
you got a boiler, that thing blows up on you too.
Yeah,
Exactly,
You don't want to be storing that, but that's why you're controlling the pressure, inlet pressure as well?
yes,
So
exactly.
you control the flow rate, so you're in contact with the heater longer?
Yes, to
Um,
increase the heat per kg.
So you're using 77 degrees for the water input?
The water
Fahrenheit?
input optimum degree would be
Usual.
20 degrees Celsius.
How much?
21-degree angle of the ball valve.
Okay, well, I mean, the ambient temperature in Miami is usually what, like 77 Fahrenheit?
77 Fahrenheit, which is like 28 degrees
Okay.
Celsius.
That's good. I thought you were gonna need a bigger heater, but now that since you're controlling the flow of the inlet.
That was the
that
key,
makes
the
sense.
mass flow rate.
Yeah, we also want to control the flow because we also want to get like a laminar flow throughout the exit nozzle. That way that the laminar flow will keep maintaining its temperature before, once it's applied to the weed.
Yeah, I was looking at your report because of that, and I mean, laminar flow, turbulent flow wouldn't be better for a heat transfer? Or?
Because it will splash. And the,
No, I'm saying inside the chamber. of the
It
heater.
would be,
Yeah.
but then there's also an issue of safety. We did present this exact concept in our senior one, and we got a lot of questions regarding the safety. If there's a high volumetric flow, then it's turbulent and there's chances of injury.
Okay.
That's why we reduced the pressure from 45 psi.
So when you stop the flow, the other end is open though, right?
Yes.
So there's no reason for it to explode or anything. You just melt it. You just melt your thing.
yeah, that's what happened with our, we had 2 previous heaters that we tested out, and that's what happened actually.
Okay.
Exactly.
Good,
Also,
good.
it's really important to have the water flowing before the heaters are turned on, because these heaters are submerged tank heaters. In an open environment, they will go.
Yeah, it's not typical.
The first one is a regular water heater and this one is a cartridge heater. So it's a different one.
Okay, could you go back to your fluid mechanics graph? There's a chart before those graphs.
Yeah. Yes.
Yeah, I'll go back, that's it. That third column, should there be a 3 there where it says mass at the top, volumetric flow?
-3? Yes.
Okay, all right. Now go to your standards chart. Oh, wait a minute, go back. All right. So from a global perspective, why would you want to put a Broward electric code in your standards?
Well, that's the one we were testing. We were testing in a household in Broward, and we just followed the codes that way because we had to use 2 heaters. One was 2,000 watt and one was 500 watt.
We felt that it's important to
Yeah.
mention on what codes that we were actually having for the time testing.
Okay, but then you have a global slide where you're talking about globalization of this concept and this product. So how would you adapt your standard to accommodate for the global perspective of the globalization of your project?
Well, the first thing would be the wattage, because let's say in Asia specifically, they don't use 220 volts, they would use 110 volts, so we would have to adjust the heaters in that manner. That would be the most important thing.
I would suggest you want to adjust it here too.
Okay.
Yes or no?
Yes, sir.
All right.
Yes, sir.
Okay.
Really quickly, what standards did you follow specifically for your design? You put these standards here, but what did you do specifically in your design to follow these standards?
Well, we followed the EPA, the United States Environmental Protection Agency. They have a huge manual, but there's one chapter, it says Chapter 6 for the Water Act. So it just says that any substances placed in there, we can't apply it to the system because that way it will affect the ground as well.
Okay.
So,
So there's 6 here, right? Broward Electrical Code. What standard did you use from the Broward Electrical Code? So for instance, you made a circuit breaker out of a piece of wood or
Yeah.
a box of wood, right? Is that up to Broward Electrical Code?
Yeah, the Broward electrical code, that means, normally the household has the outside, the GFCI is 20 amps, the inside is 15 amps. So we need to specify in the manual. So it should be 20 to 30 amps circuit breaker should be. All the outside GFI. That's we mentioned the electrical code of Broward.
So if an electrician came and looked at your specific circuit breaker right there, he would approve that for use?
Yeah, definitely.
But
That breaker, okay,
is that a fusible link you got on there?
yeah.
Yeah.
Okay, now but aren't you already have a 20 amp breaker to
Right.
that thing, right? Or already?
Mhm.
So why would you need another one?
No, this one has 2,500 watts with both heaters. So both heater.
Yeah, that'll pull around 22 watts,
Yeah.
22 amps, right?
22, 23 amps.
Right, now, what I'm asking is,
This
your
one?
circuit breaker in the house itself
Yes,
is 20 amps, usually 15 or 20.
yeah.
I don't see a 30 amp with a 110 voltage.
Yes, the inside one is 15 amps and the outside one is 20 amps. On the outside,
Yeah, but what I'm saying is you will blow the 15 amp before you blow that one. Wouldn't you? I mean, am I confused
Yeah,
here?
yeah,
Right,
no, you're
right.
right. You're absolutely right.
So you don't need that.
for the safety that we use that one for.
Yeah, but you already have a breaker in the box, in the house.
Yeah.
Uh-huh.
I guess we were just.
Unless you were using a 50 amp, then you need that. You see what I'm saying?
Oh, absolutely.
Because we did have a couple of close calls over here, but we were just being safe with it.
Yeah, for the safety, so we use
Scared?
that.
You were scared?
I don't blame you guys.
I've done worse than that.
So one other quick question for you guys. You said that you were pretty confident that 2,000 watts would be enough, right? And you said there's some theoretical calculations that you did that made it, that you felt that was some sort of confidence level. Did you go back and try to recalculate anything, or
We
you
did.
just, Okay.
I perfectly did, and I also calculated the losses. Mr. mentioned here, like
Mhm.
radiation losses.
Mhm.
I didn't anticipate that. That could be one of the causes of getting 2001 at that
That
time.
should be minimum though, because of the
Yeah.
temperature difference.
right?
Yeah, radiative
Yeah.
would be if you were at 500 degrees or something like that.
So I guess the main question is, how did you validate that initial design, right? You felt very confident that 2,000 watts was acceptable and would give you the temperature. How did you validate that number?
Of 100 degrees Celsius?